Bismillahirrahmanirrahim. Welcome to the lecture 10B of digital signal processing. I am Muhammad Atif and my registration number is 16D108. Today I will tell you about the moving average filter. The moving average filter is the most common filter in DSP because it is easiest digital filter to understand and use. In spite of its simplicity, the moving average filter is optimal for common tasks. Now, implementation by convolution. The moving average filter operates by averaging a number of points from input signal to produce each point in the output signal. In equation form, it is written as y of I equal to 1 of m summation j equal to 0 to m minus 1 x of I plus j, where x of I plus j is the input signal and y of I is the output signal and m is the number of points in the average. For example, in a 5-point moving average filter, point 80 in the output signal is given by y of 80 equal to x of 80 plus x of 81 plus x of 82 plus x of 83 plus x of 84 divided by 5. As an alternative, the group of points from the input signal can be chosen symmetrically around the output points. Y of 80 equal to x of 78 plus x of 79, x of 80, x of 81, x of 80 divided by 5. And this can be written in the equation form as y of I equal to 1 of m minus 1 divided by 2 to m minus 1 divided by 2 and x of I plus j. And here there is a transformation from j equal to 0 to m minus 1 divided 2 minus m minus 1 divided by 2 to m minus 1 divided by 2. Now I will tell you about the noise reduction and step response. The moving average filter not only very good for many applications but also optimal for a common problem, reducing random white noise while keeping the sharpest step response. A rectangular pulse is buried in the random noise in graph. This is filtered by 11 or 51 point moving average filter. As number of points in the filter increases, the noise becomes lower, however the edges becomes less sharp. The moving average filter is the optimal solution for this problem, providing the lowest noise possible for a given edge sharpness. Now, moving toward the frequency response, it is mathematically described by the Fourier transform of rectangular pulse. This figure shows the frequency response of moving average filter. The moving average filter is very poor low pass filter due to its slow roll off and poor stop band attenuation. Poor attenuation and slow roll off. That is why it is poor low pass filter. Now I will tell you about the multiple pass moving average filter. The multiple pass moving average filters involve passing the input signal through a moving average filter 2 or more times. This figure shows that the overall filter kernel resulting from 1, 2 and 4 passes. 2 passes are equivalent to use a triangular filter kernel. After 4 or more passes, the equivalent filter kernel looks like a Gaussian. Figure B shows that the multiple passes produce an S-shaped step response. The frequency response in C and D are given by Fourier transform of rectangular pulse. This figure shows the frequency response of Blackman window and Gaussian filter kernels. Both these filters provide better stop band attenuation than the moving average filter. This has This has no advantages in removing random noise from time domain encoded signal, but it can be useful in mixed domain problems. The disadvantage of these filters is that they use convolution, a terribly slow algorithm. They use convolution, that is slow algorithm. Now the last topic of today's lecture is recursive implementation. Recursive implementation is shown by this equation, and in this p equal to m minus 1 divided by 2 equal to plus 1. This equation shows the recursive implementation of moving average filter, and in this x is input and y is the output of the signal. Before this equation can be used, first point in the signal must be calculated using a standard summation, which I discussed in the previous lecture. Note that this equation uses two sources of data. Calculate each point in the output from the input and previously calculated points from the output. The moving average filter, recursive filter, is very different from typical recursive filters. In particular, most recursive filters have an infinitely long impulse response composed of sinusoids and exponential. The impulse response of moving average filter is a rectangular pulse, and that is finite impulse response. It is faster than other digital filters because there are only two computations per point regardless of length of the filter kernel. Second, addition and subtraction are only math operation needed, while most digital filters require time-consuming multiplication. Third, the indexing scheme is very simple. And the fourth one is the entire algorithm can be carried out by integer representation. Thank you very much, and that is it for today.